All right, good afternoon. It is so great to be able to talk to people and see their actual faces. It's such a great thing. Virtual presentations really, I'm tired of virtual presentations. So this is great. I'm so happy that you're able to join me this afternoon. I'm going to talk to you about work that I did at Yahoo and how we use TLS to inject security into cross-cloud workflows. A little bit about me, as folks are trickling in. I am a member of the Apache Software Foundation. I have been a Apache Traffic Server committer for a number of years. Until recently, I worked at Yahoo, Verizon Media, Oath. We've had a number of names. And I worked on the Edge team, wearing an Edge shirt here. More recently, I have moved over to Aviatrix, which is a multi-cloud networking platform company. Really fascinating stuff. Talk to me afterwards if you're interested. But the point of today's talk is the work that I did at Yahoo. And in my free time, I practice and teach yoga and take yoga pictures in scenic locations, as one does. So the goal of this talk is, I said, to present how we use TLS to move Yahoo's workflows from a single on-prem deployment into multi-cloud and hybrid cloud scenarios, and how we did it leveraging open source. And as with any non-trivial project, this was not my work alone by any stretch of the imagination. There was a goodly number of my colleagues from Yahoo and members of the other open source communities, and so I'll list a few of them there. Let me first start by introducing the open source projects that we leverage. So one of them is Apache Traffic Server, which is a project near and dear to my heart. It is a web caching and proxying server. It's been open source for over 10 years. It was originally Inktomi proxy. Inktomi got bought by Yahoo, and Yahoo open sourced that project. The interesting thing about Apache Traffic Server is that it has a plugin architecture. So the deployers of the traffic server can build plugins that get registered and get called at key points in an HTTP transaction process. So this is a good way of injecting business critical specific logic into your HTTP processing. In the last probably 4 to 5 years now, added fine-grained TLS configuration, TLS processing to support the work that we're talking about today. The other open source project that we'll be talking about and that we leveraged is Athens, which is another open source project that was contributed by Yahoo. This one's a newer one. It is a RBAC, a role-based access control system that takes advantage of TLS mutual authentication. And it's been the basis for Yahoo's service-to-service authentication. Everything has moved over to Athens. And so by using Athens and Traffic Server, we're able to perform what I'm going to talk about today. So what's the motivation? Other than this is really cool technology, what is the business case that we're solving here? So to answer that, I'm going to do a little history lesson. I decided my user agents should be happy dancing user agents for this presentation, so we've got happy dancing user agents. In the good old days, we would have everything would be in an on-prem corporate data center. And maybe there would be multiple corporate data centers, but everything is in the data center. So when the user decides to talk to finance.yahoo.com, you ask the DNS points them at a particular data center, comes in the front end. Maybe multiple services are talking to each other, but they're all within the same data center. Pretty straightforward. Good old days were pretty easy. Even in that scenario, we would have maybe caching, CDNs, ADNs, having pods that are closer to the end user. So maybe we would have an edge pod in St. Louis so that the user who's talking to Yahoo Finance maybe would first connect to the edge pod in St. Louis. Maybe the data's cached there, maybe not, and eventually go on over to the corporate data center in Buffalo, probably. But even with that complication, everything is pretty static, right? There is the edge, maybe you're bringing up new edges, but it's constant software. Everything that's deployed in the data center is staying in the data center. In the more recent past, we have public clouds, and our keynote this morning was talking about public clouds. And in that scenario, for newer companies, greenfield build-outs, you would just rent resources within the public cloud. So for example, AWS, you would build out your front-end, back-end services within AWS. And then your user agent asking for startup.com would get directed to an AWS Elastic IP address, which would go get routed to the front end. And again, everything would be within AWS, single cloud. So that is great for startups, for anyone that's greenfield. But when you have a larger organization like a Yahoo, they're not just going to pick up everything and throw it into the cloud. That's probably, maybe not ever do that, but certainly not all do that in one fell swoop. So you end up with a hybrid cloud or a multi-cloud situation. And so in that case, it's really not much different for our end users. They talk to DNS, they get an address for something, and it might route them to an on-prem server, it might route them to Azure. But they go and they make the request to that front end. But then here's where things differ, right? The back ends may talk to services in other clouds, right? Not everything's on-prem, not everything's in the same cloud, but our on-prem may talk to a service in AWS. Maybe our Azure talks to a service in AWS. Maybe that service is in AWS today, but maybe tomorrow it gets moved to Google Cloud because we got a really good deal with Google Cloud. So we have a very dynamic environment, a very dynamic trust environment. So no longer can we make, which is probably bad assumptions, that anything that's a corporate IP or anything that's in our IP space is trusted. Certainly cannot do that. You also have to deal with historical applications, right? So in the first two scenarios, we had stuff that was on-prem, probably been on-prem forever, or a new build-out in AWS. But here we're talking about moving applications from on-prem into the cloud in a hybrid cloud case, or maybe between clouds. And if you are a company that's been around a long time, you have applications, what I call here historical applications, that are making money, they're important, they're business critical, but no one really understands how they work. You can figure out how they work, of course, because it's code, you can figure it out. But in terms of quickly and agilely augmenting them to become aware of dynamic trust relationships, that's something that's not going to happen. So, dynamic trust relationships, dealing with historical applications. That is the problem that we were facing. And we addressed it by adding to our secure edge. So we've had a secure edge within Yahoo for a goodly number of years, so an ADN, a CDN. The secure edge is the point where the customer comes into Yahoo's corporate environment, historically. And so that is kind of the front-facing view that presents all the latest, greatest protocols. It runs Apache Traffic Server. It verifies that the security is good, that the headers are good. It does that first pass of making sure that really obvious malicious traffic does not make its way through. And it's the one-stop shop for our security team to start to verify that we're all running the appropriate versions of OpenSSL, we're offering the right ciphers, that everything is good in our presentation to the customer. So this seemed like a reasonable point to add, in addition to presenting and proxying communication from our end user, to also use that to proxy communication between clouds. So the client in one cloud or on-prem and the server in the other. And that's what we did. So yes, so the goal is to move our applications without, set up a scenario where we can move our applications without significant security rework. So let me take a little bit of time and review some TLS and talk about MTLS a little bit. So in the classic TLS authentication, it's an asymmetric authentication, right? Only the server provides authentication information to the client. So in this scenario, our client sends a hello, TLS hello. The server sends back a hello and sends its cert. The client checks the cert. At a minimum, it should verify that the cert is signed by a trusted CA, Trusted Certificate Authority. Maybe it checks something about the names in the cert compared to what it requested. Assuming that passes, then we do the key exchange, and in the course of the key exchange, the server is proving to the client that it owns the corresponding private key that corresponds to the server cert. So again, only the server proves the identity. If the client needs to prove the identity, that's done at a different level. So maybe using a password at the application layer. But that is not intrinsic to the TLS protocol. The TLS protocol does allow mutual TLS or cert authentication in both directions. So that's what this scenario is showing. In this case, the client sends a hello, the server sends its hello and the cert, and in addition, it sends a message saying, hey, you should give me a cert as well. The client checks the server cert as before and sends the client cert, so both sides check each other's cert, making sure it's signed, maybe doing some structural checks on the contents of the cert. Assuming they both pass, they do the key negotiation, key exchange, and in the process of that, prove to each other that they own the private key that corresponds to the cert they exchanged. So this is not something that you probably want to unleash on the end user, kind of awkward, but it is a pretty good solution for service authentication. And that is, again, what Athens built its role-based access control on top of. So I talked about dealing with historical codes, historical clients, servers. It's possible that the clients aren't capable of doing mutual TLS. Maybe it's the software set they're using. It would involve some rewrite to deal with that. So we can deal with that by putting a proxy in front of the client. The proxy then would take care of offering the appropriate certs when the server asks for a client cert. And when we started this traffic server, you could configure one cert that you're going to offer up if the server requested a client cert. And we've augmented that so that we can do a finer grained client certificate selection. Within Traffic Server, one of the core configuration files is the remap file or the mapping file. And that's the place that says, for this client request, we want to send it to this server URL. And as a part of that, we can provide overloads or overrides. So specifically here, we're showing if the client request comes in on bank.yahoo.com, we are going to override the SSL client cert file name to be pci.pem. And if the client comes in on yahoo.com, we are instead going to offer up the cert that's in datastore.pem. So it gives us that fine granularity. So a proxy can offer different client certs to different servers. You have a similar issue on the server. Maybe you have a server that's incapable of doing MTLS. So again, you can put a proxy in front of that. Now this is a little trickier because it would be easy enough to set up our proxy to say always request a client cert. That's easy to do. But what if your proxy is serving requests from end users and from services, and only some of the requests require a client certificate? Well, we can't use our remap approach because this is done before any HTTP crust is sent, right? This is done as we are negotiating that initial TLS connection from the client. So we take advantage of SNI. We do have SNI, which is server name indication. So in our client hello, there's an SNI field, which generally is set to the host that the client intends to connect to. And all modern clients do this, your browsers do this, curl does this, old TV sets don't, and some load balancers don't, but modern clients do send an SNI. And so with our first packet, we can look at the SNI and we can say, okay, well, based on this SNI, SNI request to server secure.com, I want a client cert. Maybe other domains, I know they don't support HTTP2 very well, so I'm going to adjust my ALPN and say I'm only going to do HTTP1 to you. So very handy to take a look at that SNI, and we have a whole sni.yaml config to adjust these different parameters based on the SNI name that is received from the client. So great. The end of talk. We're all done, right? Yeah, no. Problem is, SNI isn't really a secure field, right? It's showing up in client hello. It's in the clear. The client can set whatever SNI name he wants to set. It's really just convention. That's the domain name he wants to talk to. So it'd be easy enough for a malicious client to set the SNI name to some other value. So if our malicious client knew that we were using SNI to set our security policy to determine that we need a client cert, so example, we have a policy that says any requests for secure.com need to provide a client cert. It would be trivial for our malicious user to instead set an SNI to insecure.com. There's no policy for that. We do the TLS negotiation. No client cert is requested, and life is great. And then they send the request for secure.com. So we've had this break. We're conflating what's happening in TLS land with what's happening in HTTP. So unless we come back and check that, if we just merely move along independently, our server would just return the sensitive information from secure.com and be pretty easily tricked, right? And it's just trivial. This is not a super hacker kind of move. This is the curl command to do exactly that, right? You set the host header, the SNI name is pulled from the URL. There you go. Well, that's a bummer, right? So what can we do? So there's a couple options. The first option is say, well, that was really stupid to use SNI, not secure, just give up on that, and we'll have one proxy set up for things that require client certs and another one for things that don't. And we'll adjust our DNS and we'll deal with it. So that would work, of course. It's a little awkward, but it would work. The other option is to say, well, I said the issue is that we're doing checks across levels, right? Across TLS and across HTTP, and we're not bringing them back together. So let's bring them back together. So option 2 says, for every transaction, we should check to see that the host header value is equal to the SNI value, and if it isn't, then we should return a 403 or some sort of error code. That would be safe, right? And that would enforce our assumption that those two values are consistent. But that is probably too onerous, specifically in the browser case. And if there was no SNI policy for any of the names involved, then it really doesn't, it over errors, right? So here I show a browser and a server, and the browser negotiates with foo.com, does a TLS handshake, because there's no policy for foo.com, so no client cert. Does a request for foo.com, gets a response, and then reuses that connection later because the cert also contains bar.com and makes a request for bar.com. So if we're checking that every single request has a host header that matches the SNI name, then we would have to reject bar.com, even though there was no SNI policy for foo.com or bar.com. So, and that definitely happens. So we can't do that either. So what we ended up doing in Yahoo with Traffic Server is probably what you would think if you take half a moment, right? We negotiate, we get a request. We then take the host header once we get the request and say, was there a security policy associated with the value of the host header? In this case, secure.com. And in our scenario, yes, there was. If there was a security policy or an SNI policy associated with secure.com, then we need to do the name check. If there wasn't, we don't care. Merely, we would move along. So in this case, our malicious user would get caught because there was a policy, an SNI policy associated with secure.com. The names don't match with the SNI policy. We would return a 403. And this has worked very well for us. We get very few false positive errors, and we catch our malicious users who are trying to evade policy. There are some other options and there's a draft RFC here that talks about them in detail. But the idea here is that we really should be doing this at the HTTP layer. This kind of cheating and reaching down to the layer before is a little dicey. You can actually do this for HTTP1. So with HTTP1, there is one request going on at a time over the connection. And with renegotiation in OpenSSL, we can go and request a new client cert after the connection has been established. So in this case, we have our example with an SNI with insecure.com, handshake, then getting a request for secure.com. And at that point, we could go and request a client cert for secure.com. And if they brought it, then it would be great, and we could move on. So that works for HTTP1, does not work for HTTP2. Because with HTTP2, you can have multiple simultaneous active transactions over your TLS connection. So if you're doing this one-off request for the next client cert, well, which transaction did that belong to, right? Just not something that's going to work unless you bring in some cert requesting logic into the HTTP2 layer, which is what that RFC is suggesting. And so if they come through with that, if they agree on it, and it gets implemented and deployed, that is probably a better solution. But in the meantime, the solution that I outlined has worked pretty well for us. So that's kind of the basis of the TLS kind of things that we're doing. So how are we using that to build our proxy TLS? So as I said before, the goal is to support dynamic trust relationships where the client is in one cloud and the server is in another cloud. So we don't want to directly expose our servers to the internet. So we have this kind of secure edge idea. And as we noted before, some client-server implementations may have some issues that we need to kind of fix up for them. So we don't want to directly expose them to the outside world. So there are three options. There's TLS Delegation, tunneling, and bridging. And we'll talk through each of those. Before I go into the TLS Delegation, let me talk a bit more about how Athens performs its authentication and authorization. So as I've said now several times, Athens builds on top of TLS mutual authentication. So the client, again, provides a 509 cert that's signed by the Athens CA. The valid cert also contains a Athens principal. Then after the connection is set up, each request will come in with an Athens token. And the token identifies the principal and the roles that principal is authorized for. And so that would have been fetched at the point of the client request. We would have talked to the Athens infrastructure and gotten a token to pass along. The token has a limited lifetime and it's signed, and as I noted, passed in the head of the client request. So in the Athens case for TLS delegation, the client is going to talk to the proxy, and the proxy will send back a proxy server cert. It's going to request a client cert, and so the client will send its Athens cert up. The proxy then is going to perform an authorization check over the client cert. So it's going to verify that the cert is signed by the Athens CA. Assuming it is, we're going to go ahead and complete the handshake, and the client will send a request. The request will contain an Athens token, A. And then the proxy is going to do another authentication check against the client cert and A. So it's going to verify that the principal in the token matches the principal that was in the client cert, and it's going to verify that the token is well-formed, so it's not expired and it's signed correctly. Assuming that all pans out, then it's going to turn around and make a connection to the server. The server is going to send its cert down. The proxy is going to send a proxy client cert. So it can't send the original client cert up because the proxy does not know the private key of the client cert. So it's sending up a new cert telling the server that, hey, I'm the proxy. And the server will do a verification on the proxy client cert, verifying that it's signed by Athens. Assuming that finishes out, we complete the handshake, and the proxy is going to go ahead and send the request up with the original token and a new header that indicates that it has validated the token. And then the server will do a second F2 prime, verifying the proxy client cert, the token, and the validation header. And assuming that all checks out, we'll send the response will go back to the client. So with this, the server has delegated authentication of the client's Athens cert to the proxy. So what happens if the malicious user decides, well, hey, maybe it's an easier idea if I can get around and pretend I'm the proxy? Is that going to make life easier for it? So there's several things that make it more difficult for the malicious user to bypass things. So if I'm the malicious user and pretending to be the proxy to try to negotiate to the server, I'm going to send up my malicious cert. And I need that malicious cert to pass the check that the server is going to make. So I need to make sure that it's signed by a trusted CA, the CA that the server trusts. If the server is set up just to trust our Athens CA, then that should be pretty good. Our malicious user could possibly steal a proxy cert from someplace else, but that's another issue. If our server is misconfigured and it has too many trusted roots, maybe it trusts the standard Linux set of certs, so DigiCert, then it would just be an issue for our malicious user to spend $50 and get a DigiCert cert that would pass signature verification. So don't do that. Make sure that your server is trusting a limited set of CAs. So hopefully we get knocked out in our first check there. But if we move on, then the malicious user could make a request with a token and a verification header. It will probably have to have stolen a token because, again, the tokens are signed and they're limited lifespan. So even if it's stolen, it shouldn't last for very long. So anyway, there are two levels of making life difficult for a malicious user here. So that's delegation. The other option that we have is TLS Tunnel, which isn't really proxying. It's really just routing. But the motivation here is that there are certain requests that, for example, that are supporting PCI or SOX compliance that really we do not want to terminate on our edge, because that means that we would have to go through and do PCI compliance checks on our edge, and that seems like a really unwise thing to do. So in that case, we can set up our SNI policy to say, for supersensitiveexample.com, just route all the connections to supersensitiveorigin.example.com. And so in that case, the proxy is just moving the tunneling packets, that's the TLS packets from the client to the server, not doing any checks. So not a super satisfying solution, but something that gets things going. And one of the issues there is that we don't have any control of the quality of the TLS connection between the client and the server. We're just blindly moving things along. If we wanted to avoid decryption on the proxy, but we wanted to make some guarantees of the strength of the connection between the clouds, then the TLS Bridge solution would work. And the idea with the TLS Bridge is that the request comes in, it's labeled ingress, but as we're leaving one cloud, and we have a plugin that's set up to recognize that the client is going out to a server that's in another cloud. And so the plugin will stop that using one of the transaction hooks and negotiate a new TLS tunnel with a peer in the other cloud. And with this tunnel, we have control over using mutual TLS, having a strong cipher, making sure that everything is good. After that tunnel is set up, then the ingress ATS will, again, blindly take the packets from the client, pass them along our new TLS tunnel. They'll pop out the other end at the peer ATS and get sent to the service, and ditto traffic going back. So we are probably double encrypting the traffic that's going across the untrusted cloud, but we are sure of the strength of the traffic. This is just another diagram explaining the same thing in a different way, so we'll move on. So wrapping up, the secure edge approach, using the secure edge to inject TLS mutual authentication has been instrumental in Yahoo's move to a hybrid cloud. This proxy provides our one place to ensure that our security policy is applied consistently. We can use the proxy to help move forward our historical applications more quickly, so not everyone has to become mutual TLS experts right away. And if we set things up correctly on our ingress and egress edges, moving clients and servers between clouds and having the dynamic trust authentication, the Athens authentication happen should be much less of an issue. And I think I must have talked really fast because that's all I got. Are there any questions? Yeah, so certainly one can do this at different levels. And yeah, Yahoo has a, how to phrase that? They like to kind of do things with chewing gum and string, right? So doing it at the transport layer was kind of convenient because we already had this transport layer infrastructure set up with our edge. The other way that you could certainly do things is going down a layer and either buying, doing IPsec layer stuff. And actually, interestingly enough, at my new company, Aviatrix, we were working at that IPsec layer, WireGuard layer. So that is certainly a different approach, a reasonably valid approach. You would still have to deal with the authentication. So that would just deal with the encryption. Depending on what kind of IPsec you're using, you could maybe get your authentication at that layer too. But that would be something that you would have to think through. So yeah, you certainly could do this at a lower layer. If you're doing historically kind of data center to data center, they would just buy hardware encryptors and do that between the data centers. But again, no authentication, although that's less of a concern between data centers. Much more of a concern going between clouds or between data center and cloud. Does that answer? Yeah. It is, yeah, a huge thing with Athens because they are generating certs, I think, on an 8-hour basis, right? So I don't, again, the Athens was not the part I was super involved in. I don't think they were leveraging cloud-specific services for that, but I'm not super sure on that. But yes, that dealing with rapid certs, not even from a cert generation perspective, but the bigger issue is the distribution perspective, right? And with the Secure Edge too, that's something, our server cert lifecycle in my time with Yahoo went from like, yeah, maybe once a quarter or so we'll update all the server certs to 3 weeks, and they're trying to grind it down. So, faster and faster. And so to do that, once a quarter or so is ops guys making sure everything's set up correctly, pressing the button, hoping. But to do anything faster, you have to really do a lot of automation. And that's where certainly Athens is a lot of automation. And as I said, with the server cert distribution too, we're doing a lot more automation, a lot of probing our central secret server to fetch the information and update things live without requiring reboots and such. All right, last call for questions. All right, well, thank you so much. And reach out to me later if you have any other questions.